Okay, next I'd like to look at the Earth, and so you might wonder, well, this is an astronomy class. Why are we talking about the Earth? By definition, astronomy is everything outside of the Earth. And that's true, but we can learn so much about the other planets from studying the Earth, because the Earth is the planet that we know the most about. And we can also learn a lot that can be applied to the Earth by studying the other planets. So it's an important give and take. And the Earth is the largest of the inner planets and is the only one with a moon, and as far as we know is the only one, at least with advanced life. And we'll have to wait and see whether there are more primitive forms of life on places like Mars or Venus. But in terms of its interior structure, let's start with that. We have an inner core. This is mostly, it's solid and made mostly of metals, denser materials. Compounds of iron, nickel, magnesium, stuff like that. And it's solid. The outer core is liquid. It's similar in composition to the inner core. Now there's some evidence that the inner core may have solidified about 600 million years ago, and that contributed to the development of a stronger magnetic field on the Earth. And interestingly, around that same time is when we had what's called the Cambrian explosion, in which huge amounts of diversity of life started to develop all over the surface of the planet. And so there may be something significant about the protective influences that a magnetic field can provide. And this phase change, which some scientists now believe happened something like 600 million years ago. And then surrounding the outer core, we have the mantle. The mantle is made mostly of rocky materials. Called silicates, which are combinations of silicon and oxygen. Like silicon dioxide, for example, is beach sand, it's quartz crystals, but you have more complicated combinations of silicon and oxygen that can form under pressure. But despite the fact that you see magma shooting out from the mantle and being liquid, under pressure it's a solid. So the inner core is solid, the outer core is liquid. And it's thought that motion in the outer core may help to give rise to the Earth's magnetic field. Okay, and then surrounding that, we have what's called the lithosphere. Here I'm greatly exaggerating its thickness. It's only about 100 miles thick. We compare that to the radius of the Earth, it's about 4,000 miles. Okay, so here this is only, what, 1/40th as big as the distance to the center. But this is where we live. And so this floats on the mantle. And parts of the lithosphere are broken up into pieces called plates. And these plates then can move around because of the release of heat from the interior. So they're like little boats floating on the mantle. Remember, this is by radioactive decay that this heat is released. Okay, and so the lithosphere then is broken up into little pieces. And those pieces then can float around on the rest of the mantle. So if we look up at the data projector, we see here the iron core, and then we see some mantle plumes that are sinking down that have cooled, but then we see other mantle plumes that are rising up toward the surface. And so these can be the source of the heat, which then tends to drive the plates around. And so here we have the solid iron inner core. Here's our liquid iron outer core, the mantle, and then the crust is the upper part of the lithosphere. The lower part of the lithosphere is the part of the upper mantle that's frozen onto the crust. And so both together, the crust and that little piece of the upper mantle that's frozen onto the crust is what we call the lithosphere. And so we have different kinds of plate interactions that can take place. Near a continental margin, we have ocean plate material that can dive beneath the surface of a continental plate to create what's called subduction. And then on the return of this material, which is melted at depth and then been circulated back around, it can rise up, create volcanic reactions along what's called a rift zone. So let's just take a look at those different kinds of plate interactions that can take place on the Earth's surface. One type is, well, let's take a look at the different types of plates. We have a continental plate, which is lighter, kind of like lunar highlands. It's lighter material and it's lighter in color too. And it floats higher on the mantle. And here we have oceanic plate. And so it's heavier, more dense, darker in color. Just like the Maria regions, they tend to sink down. Remember how those Maria regions would sink down and the lunar highlands would be higher up? Same kind of thing here on the Earth. The ocean plate is kind of like the Maria. It's heavier rock, more iron in it. It's more of a basaltic composition, where this is lighter color, more granite composition with less iron. And iron is heavy. So these oceanic plates then tend to be heavier. So when they come into contact with the continental plate, because of the release of heat from the interior, then we get what's called subduction. And in subduction, the heavier ocean plate sinks beneath the lighter continental plate. And so for this reason, the ocean plate tends to be a more temporary kind of a structure. Now, as the ocean plate dives, it melts at depth. And it's helped by water. Water in the oceanic plate material helps it to melt at a lower temperature. And then after about 10 million years, this magma starts to work its way up toward the surface and create continental volcanoes. So these are explosive and unpredictable, like Mount St. Helens. In the Pacific Northwest, we have Mount Lassen, Mount Shasta, Mount Hood, Mount Rainier, and St. Helens. Those are all still active volcanoes that are caused by the subduction of the Pacific plate beneath the North American plate. And so this tends to build up. There's also a crunching effect here. And so this is what has created the coast ranges along our part of the California coast. And so that is one type of plate interaction, is what's called subduction. Another type is called spreading center. And so here the plates, and typically this can happen in an ocean plate. The ocean plate is being pulled apart. So let's say over here this is South America, and over here this is Africa. Then as those plates are being pulled apart, South America is getting farther apart from Africa. You don't have to be a jigsaw puzzle expert not to have noticed that the African coast and the South American coast kind of fit together. And so as it turns out, they'd noticed this a long time ago, but it wasn't until the 1960s that they came up with a mechanism for how plates can essentially be floating on solid rock and moving through solid rock. How does that work? And so they finally discovered that they think that these plates have a partial melt zone of only about 2%, but it's enough to allow for the plates to move at about the rate that your fingernails grow, which doesn't seem like much, but over tens of millions of years you can open up whole ocean basins with that. And so maybe 70 million years ago or so, the Atlantic Ocean wasn't very wide, and turtles were swimming across to lay their eggs on, let's say, South America from Africa, and then swimming back again. It was no big deal for them. But because the plates only moved a couple inches a year, they didn't really notice over all of the hundreds of thousands, millions of generations of turtles. So now these turtles have to swim across the whole Atlantic in order to lay their eggs. And so these turtles are in super good shape. Okay, so here then we have South America and Africa moving apart, and so this creates a void here. And so the plates split apart. And new plate comes in to fill the void in the form of magma. So this magma then comes in and creates these underwater volcanoes, and that builds on to the plate. Then the plate moves a little farther out, like this, and then this material is there, and then more plate comes in to fill the void. And so this is a place then where new oceanic plate is formed. And we should mention that only the Earth seems to have this kind of plate interaction, and it seems like it may be somewhat unusual. Even on the Earth, a few billion years ago, there may have been too much heat released from the Earth's interior, so that the Earth actually had to cool off a little bit before it could click into gear. It's kind of like a bowling ball that is sliding in, rolling at first, and then it goes into a pure rolling mode. It's like it took a little bit of cooling of the Earth's interior before the plates could start moving in a well-organized fashion. But it seems like this is very, very important on the Earth for being able to maintain life, because this recirculates material and brings new material up to the surface, takes old used up nutrients and material and sinks it back down into the Earth and then brings it back up again. So it's like a rebirth. You get new crust being formed all the time, and old crust is destroyed. And so this seems to keep things freshened up and allow for the raw materials for life not to be exhausted, as would be the case without plate motions. Okay, and so this new plate material is formed here, but here ocean plate material is destroyed. Now, ocean plate material is not ocean plate because it has ocean on it. It's ocean plate because it sinks down deeper into the mantle. It's like a weight on a sponge. It's going to cause the sponge to sink down deeper into the water, and there's more weight in the ocean plate. So it sinks down deeper because there's a lot of water on the Earth's surface. It naturally goes to the lowest topographic points. And so that's why the ocean plates are covered with oceans. Okay, and so we can look here again at the data projector. We can see how we get these mountain ranges at the interaction between a plate junction and for the Pacific plate and the North American plate. But then over here, this kind of a rift would be associated, say, with the Mid-Atlantic ridge here. Okay, so the Mid-Atlantic ridge is a spreading center zone in which the plates are being pulled apart and new plate material is coming in to fill the void. And so here's a picture of the different plates on the surface of the Earth. Here we have subduction taking place along the Pacific plate north of the town of Mendocino in California, and also a lot of subduction taking place in the Nazca plate as it sinks beneath the South American plate. And then over here on this side too, this is called the Ring of Fire around the Pacific Ocean, because of the fact that you also get subduction in this direction with material from the ocean diving beneath the Eurasian plate. And then there's a third type of plate interaction called strike-slip. So in strike-slip, we see here that the plates move laterally with respect to each other. So in our part of California, the plates are moving north, kind of north east. And on the other side, the San Andreas Fault, the other side of Parkfield, and then this makes a little bend down here. It's moving more in a southwesterly direction. So in strike-slip then, for example, along the California coast, the plates move sideways or laterally with respect to each other. So the San Andreas Fault then is an example of this. Whereas here, an example would be the Mid-Atlantic Ridge. And an example here of the subduction would be active volcanoes in the Pacific Northwest. So that would be anywhere north of Mendocino, California, you get this kind of subduction. And so here then, with our strike slip, this is interesting to us because every time there's a little earthquake, we move a little closer to San Francisco. So we think that the drive from LA to San Francisco is going to be much shorter. In about 5 million years, you won't hardly have to go anywhere at all in order to get from here to there. And so these then are 3 of the most important plate interactions on the Earth's surface, but are not seen on the other inner planets. Okay, so there's one type of mechanism on Earth that is seen on Venus and Mars. And this is called hotspot volcanics. In hotspot volcanics, we've already discussed Olympus Mons, its relationship to the Hawaiian island chain. Here we have a hot spot on Mars. So we have this heating of the surface generating gigantic volcanoes. On the Earth, the plate moves out from under the hot spot. We have the moving plate here, and so here we have Kauai, Oahu, Maui, and then right over the hot spot now we have the Big Island. So this is where the current volcanics are happening, but we have a moving plate moving over the hot spot. Whereas on Mars, the plate is stationary. And on Venus too. We think the plates are stationary on Venus, but there are certain areas where we've got big buildups of mountains and not so much anywhere else. And so this is the one type of plate mechanism that the Earth has that is seen on Venus and Mars. But what this is showing us is that the other types of plate motions that are seen on the Earth may not be as common for other worlds. Now on the Earth, something like 250 million years ago, all the continental plates were in one spot. And so this is called Pangaea. And then as time went on, Pangaea started to split apart until finally, and so this is because of spreading center zones that then tended to open up these ocean basins. We eventually end up with the Earth's land masses the way that they are today. But in the future, we think that the Earth the land masses may start getting closer together again. And so this is a much more dynamic kind of a crust than we see on any of the other planets in the inner solar system.